My name is Chan Kim in Tokyo Metropolitan University. I'd like to introduce our TMU NMT system submitted for the patent task of the WAT 2020. At first, I'd like to explain about Korean Hanja and Japanese kanji. In Japanese, many words are composed of Chinese characters called kanji. And also, in Korean, many words are classified as Sino-Korean words, which differs to Korean words of Chinese origin, and they can be converted into Hanja words. I summarized an example of conversion of SK words into Hanja in this table, and they are compatible with Japanese kanji words. Some studies have focused on exploiting Hanja information, and Park and Zhao used the parallel data in which the Korean sentences of SK words are converted into Hanja to train a Korean to Chinese translation model. In addition, Yo et al. Proposed an approach of training Korean word representations using the data in which SK words were converted into Hanja words. However, there is still no research on the NMT between Korean and Japanese using Hanja information. Therefore, in this study, we examine the effect of Hanja information in a Korean to Japanese translation. To train the translation model using Hanja information, we propose two approaches. In addition, JPO patent corpus consists of 4 domains. Therefore, we also did domain adaptation. Our experiment showed that Hanja information is effective for Korean to Japanese translation within a specific domain. And our experiment showed that the translation model using Hanja information tends to translate literally. Next, I'd like to explain our methods in detail. At first, we proposed Hanja conversion model. In this model, we converted SK words written in Hangul into Hanja via pre-processing. This table presents an example of Hanja conversion, and we trained the translation model after the conversion. Next, I introduced the Hanja loss model. Lampu and Koneu improved the translation accuracy by fine-tuning pre-trained XLM, and they observed that the bilingual word embeddings are similar. Based on this fact, we hypothesized that if the embeddings of each corresponding word become closer, the translation accuracy will improve. In the Hanja's model, to make the embeddings of the SK word and its corresponding Japanese kanji word closer to each other, we used the following loss function. And this loss function decreases when the SK word and Japanese kanji word vectors become more similar. Additionally, we did domain adaptation. JPO patent corpus consists of 4 domains, and Hanja information is more effective when the terms are derived from Chinese characters. Therefore, we expected that the effect will be different per domain. To examine which Hanja information is the most useful in each domain, we fine-tune the model pre-trained by all training data using domain-specific data, and translate the test data for each domain using a domain-specific translation model. To split the training and development data into 4 domains, we're using domain information. For testing, there are test N1, test N2, and test N3 data in the JPO patent corpus, and we split the test N1 data using domain information. However, test N2 and test N3 do not have domain information. Therefore, we train a domain prediction model by fine-tuning Korean or Japanese words using library training data of the JPO patent corpus to predict the domain information of test N2 and test N3 data. We evaluated domain adaptation model on both per domain and combined data. For evaluation of the per domain data, we translated the per domain data using domain-specific translation model and calculated the evaluation scores of the translated per domain data. For evaluation of the combined data, we combined the translated per domain data after translating the per domain data. Next, I talk about experimental settings. For implementation, we used full-stack implementation of the transformer architecture for the baseline and Hanja conversion models, and extended the implementation for the Hanja model. In data preprocessing, for the baseline and Hanja models, we tokenized Korean and Japanese sentences using Mekabu and applied shared BPE with a 30,000 merge operation size. For the Hanja conversion model, we converted SQ words into Hanja using Hanja tagger and normalized Hanja and Kanji in parallel sentences into traditional Chinese using OpenCC. After normalization, we applied the same preprocessing with the baseline model. Next, I show the experimental results. This table presents average BLEU scores of the four models. The Hanja's model achieved the highest scores of the DEP, test N1, and test N2 data. By contrast, the Hanja conversion model scores the worst. The reason for these results is that there are some errors in Hangul into Hanja word conversion, and these errors reduce the translation accuracy. Next, I show the BLEU and library scores of each ensemble of four models. The bottom two rows are the scores of domain adaptation ensemble models, and Korean BERT and Japanese BERT represent the experimental results using the domain prediction models. Looking at this table, there is no model that scores consistently better than other models across all evaluation data. Therefore, this table indicates no difference between the baseline and Hanja loss models. Next, I show the per-domain BLEU scores. This table presents the per-domain DEP and test-N1 BLEU scores of each domain adaptation model and each model trained by per-domain training data. In the domain adaptation setting, there is no difference between the baseline and Hanja's model. However, when we only use the per-domain data for training, the Hanja's model achieves the highest scores in the mechanical engineering and physics domains. This result indicates that the Hanja's model is effective in the mechanical engineering and physics domains when only per-domain data is available. Finally, we show an output example of the Hanja's and baseline models, and we indicated the bilingual words as the same colors. As a difference of translation between two models, the baseline model cannot translated the word tansondo, which means single yarn fiber, but the Hanja's model can translate it correctly. In addition, the baseline model translated the word sayon, which means use, into mochi, whereas the Hanja's model translated it into shio. And these words of the Hanja's translation, tanshisendo and shio, are the Hanja forms of the SK words, tansondo and sayon. Therefore, this output indicates that the Hanja's model tends to translate literally. So in conclusion, we propose novel methods for training the Korean to Japanese translation model, which uses Hanja information. The Hanja's model is effective in the mechanical engineering and physics domains when only per-domain data is available. In addition, the Hanja's model tends to translate literally. For the future works, we found that the Hangul into Hanja word conversion errors reduce the translation accuracy in the Hanja conversion model. So we would like to develop a method to mitigate conversion errors. And many Hanja and Kanji words are of Chinese origin. Therefore, in the future, we will attempt to develop a translation method that takes advantage of the vocabulary overlap among Korean, Japanese, and Chinese. And this is the end of my presentation, and thank you for the listening.